Good afternoon, folks. Welcome to today's problem. I realize this may be a bit of a surprise with the new format, but hopefully you will consider it an upgrade, like I do. Let me know in the comments. In any case, moving on to our problem, we have a 3-kilogram box that is several hundred meters above the surface of the Earth, and it's suspended from the end of a short vertical rope of negligible mass. There's a time-dependent upward force being applied to the upper end of the rope, and this results in a tension given by this expression here. We're told that the box is at rest at the initial time, t is equal to 0, and there's only two forces acting on the box, the tension in the rope and the weight due to gravity. In part A, we need to calculate the velocity of the box at these two separate times. In part B, we need to calculate the maximum distance that the box descends below its initial position. And in part C, we calculate the value of t where the box returns to the initial position after it turns around and starts moving in the opposite direction. So before we calculate anything in part A, we need to do some prep work. We need to figure out the free body diagram of the box. We need to do the sum of the forces on the box with Newton's second law, and we need to get an expression for the acceleration, because we can't do any kind of kinematics here. There's no constant acceleration occurring with this time-varying tension. So if we draw the free body diagram at different times, notice there's something interesting going on here. At the initial time, the box is being pulled down by the weight. 1 second later, the tension kicks in, and it starts to be pulled less in the negative direction. 2 seconds later, the tension is actually stronger than the weight, and now it's being pulled up. And then from then onward, it's just going to be pulled upward faster and faster and faster, harder and harder, because the tension is greater. And so the real question is, what do we do here? We haven't had a situation like this where the tension vector rather was variable. Usually it just was a static value, and we could apply Newton's second law really easily, balance things out, and we'd be done. So what's the deal here? How do we do this? And one thing that I would recommend is just draw the coordinate system like you would anyway. We have the x and the y in their familiar positions. Weight is still in the same position, but instead of the tension just being capital T, we're going to write it as capital T as a function of t, because the net behavior of the tension is going to be positive. So we'll just draw it in the positive direction. And similarly, there's going to be a net overall acceleration in the positive direction once there's enough time occurring. So we'll draw that in the positive direction off to the side too. With that done, we can move on to the sum of the forces on the box. So let's actually put this free body diagram off to the side for now, and let's pull F equals ma off of our tool belt. We want to apply this to both directions. In the x direction, it's pretty simple. There's nothing occurring, so the sum of the forces in the x direction is 0. And there's a reminder. The box is only moving in the vertical direction. On the other hand, in the y direction, that's where the meat and potatoes of this situation is occurring. We have the tension as a function of time acting in the positive direction, then the weight acting in the negative direction, and then we've got the net acceleration on the right hand of the expression over here. So what are we going to do? We need to divide both sides of this expression by the mass, because our goal is to have an expression for the acceleration. That was kind of step 3 of our prep. So if we do that, here's what that looks like. And now we have an expression for the net acceleration of the system. However, it's not simplified. It's still very symbolic, and we can do some algebraic manipulation to uh, make it look more straightforward. And so if we simplify our expression, let's rewrite it where we exchange the weight for mg, because that's what weight is. It's equal to mg. We're going to divide both pieces of what's inside the parentheses by the mass. And if we plug in the numbers for that, we have our 36 Newton per second times time for the tension as a function of time. The mass is 3 kilograms. And for mg, well, the m's canceled off, so we're just left with g. And we can plug in the number accordingly here. And this is our expression for the acceleration, 12.0 meters per second cubed times t minus 9.8 meters per second squared. And in case you're not familiar with how I went from Newton per second divided by kilogram to this expression here with meters per second cubed, here's a quick reminder. You know, we have the expression for newtons, and we have a simplification of the expression for Newton per second. So if we take that expression and divide it by kilograms, we end up with meters per second cubed. And that's what we were looking for. That was the big piece. So with that done, we can enter into the realm of calculus to get to a velocity, because that's what we need to answer part A. Part A says, what's the velocity at these two times? Well, we don't have a velocity yet. We have an acceleration. So let's integrate the acceleration expression for a velocity, and that's what this looks like. We need to integrate acceleration with respect to time, and we also have to account for any kind of initial velocity in the y direction. Well, thankfully, there is none. This ends up becoming 0, and we just plug in our acceleration expression here, and that's it. And in case you may be wondering, you know, hey, why is this 0? Well, the box is at rest. It can't have an initial velocity if it isn't moving, and it's at rest. So with that in mind, let's go ahead and simplify this integral a little bit rather than jumping in all at once. And we'll separate it into two integrals and factor out the constants. So here we're integrating just t with respect to time, and we're multiplying the 12 meter per second cubed out in front, and we're going to subtract an integral of just 1 multiplied by dt with a factor of g out in front. And what does that look like? Well, this right here. And just as a reminder, in case you're not familiar with integration rules for variables of powers or constant values, here's a reminder. This is what it looks like. Here we're integrating t to the power 1, and so you can see here t to the 1 plus 1 is t to the power 2, and this is how I'm getting t to the power 2 divided by 2. And likewise, we're integrating just 1 dt, and that's equal to t, and that's how this factor of t gets slapped onto g. So we have our velocity expression. We've done, 16 years of prep work now. We can finally get to part A. Let's do that. So here's part A. We were asked to figure out the velocity at a time of 1.00 seconds. So we're going to plug that in everywhere we had t. And what does that look like? Well, we're taking 6 meters per second minus 9.8 meters per second. And that's equal to negative 3.80. And that's one of our solutions. We have to get the other one, though. We have to get the velocity at 3 seconds now. And it's the exact same process, but instead of entering 1 second in for t, we're entering 3. Same idea. So it's 54 minus 29.4 meters per second, which is 24.6. And that is the other solution for part A. And part A is now done. But what about part B? Well, unfortunately, we need to have some setup for that as well. And I've provided a picture here that shows the behavior of the box over the first couple seconds. So as you can see, there's no tension right away, so the box is just falling. And then it falls slower when tension starts to trickle in slowly, and then it stops temporarily and reverses direction. So the idea here is, hey, you need to notice the y component of the velocity here is equal to 0 as the box turns around. We essentially have the inverse situation going on of a projectile from projectile motion. And so we are going to use that to figure out when that occurs in time, and we'll plug that into a position equation to answer this part. So first off, let's solve for the time from the velocity expression. We'll start from the entire thing, and we're going to set it equal to 0. Since we have a t squared here and a t here, I would recommend factoring out t like this. Oh, pardon me. Factor out a t. So then you have two solutions, and one of them I kind of jumped ahead to accidentally here. The first one is t is equal to 0, right? We have this as a possibility, which we don't want because we're not interested in what happens at t is equal to 0. We're interested in what happens later when the box turns around at some other positive time. So instead, we're going to take the inside portion of the parentheses and set that equal to 0. We move g to the other side, and then we divide both sides by the 6 meter per second cubed to get t. And if we plug in the 9.8 meter per second squared for g and do our math, we end up getting about 1.63 seconds if we answer this to 3 significant figures. But this is not the answer to part B. We're just going to use this to get to the answer to part B. We need to do a little more calculus before we can finish. Our next step is to integrate velocity for position. So now, if we want to get the position function as a function of time, we're going to integrate the velocity, the y component of the velocity with respect to time, and we need to account for any kind of initial displacement in the y direction at t is equal to 0. Well, thankfully, there is none, and we can just plug in our green velocity equation that we solved for previously. And just as a reminder, kind of like before, why did we set this equal to 0? Well, because the box is at rest at t is equal to 0. Everything is 0, so that makes things really easy. Similar to before, I'm going to break up this integral into 2 pieces so it's easier to digest, and that way you can clearly see we're going to be taking the integral of t squared with respect to t and just t to the first power with respect to t here. And it uses the same power rules that we had in the previous slide, so nothing changes there. And that gives us this expression, which we can simplify a little bit and plug in our values, which leads us to the final position equation, which I've colored in blue here. So what are we going to do? Why did we even do this in the first place? Well, we are going to plug in our time that we solved for in the last slide here to solve part B. And that's what this looks like here. Here's our position equation. We plug in 1.63 seconds everywhere we see t, and we get negative 4.36 meters as our answer for part B. And that makes sense. We expect it to be a negative number because we know the box drops down below the initial position before rising and coming back up again. Speaking of the box dropping down and rising back up again, we have one last part, part C. We need to set the position equation equal to 0 and solve for the time for when the box returns to that initial position. That's what part C wants us to do. It wants us to get a time. And so if we grab our blue position equation that we did all that work for, and we set it equal to 0, here's what we can do. We have a t cubed and a t squared in this expression, so we can factor out a t squared. This leads to two separate solutions, kind of like we had in part B, where on one hand, the t squared equals 0 will lead you to the conclusion that t is equal to 0. And that tells you, hey, at t is equal to 0, it's at the initial position. Okay, great. We don't care because we want to find out when it comes back to the initial position. This is not a useful solution here. We're going to throw this one away. Instead, we're taking everything that's inside the parentheses there and setting it equal to 0. And we're going to solve for the time. I move the 4.9 meter per second squared to the other side, and then divide both sides by the 2 meter per second cubed quantity. And this tells us the time. It takes 2.45 seconds for the box to drop down and return back up to y is equal to 0. And that is our answer for part C. And just to recap, I think something that is helpful here is a final kind of solution slide. For part A, we had these answers here. For part B, this was the solution. And for part C, this was the solution. So let me know if you've liked this format. Thank you for watching.